You know that highly specific, incredibly frustrating purgatory that really only developers seem to experience?
Oh, I know exactly what you're talking about.
Right. It's that moment when you change just like one single line of code. You hit compile and then you're just sitting there.
Yeah, just staring at a progress bar.
Exactly, staring at the screen, your laptop fans spool up, the
Mm.
chassis gets uncomfortably hot on your desk, and you are trapped. You're just waiting for your machine to churn through literal mountains of
Is
text.
the universal developer bottleneck,
Yeah.
honestly. Entire afternoons are lost to that waiting game,
Oh,
to the
completely.
point where it almost feels like an unavoidable physical law of software engineering. Like the larger your project grows, the slower you move.
But today, we're actually challenging that assumption. We are exploring the notoriously painful, slow compiling world of C++ header only libraries, and more importantly, how you can actually escape it.
Which is a huge topic.
It is. So, the mission of this deep dive is to unpack a 2026 case study by a developer who goes by the handle at LUK036.
Right.
Their piece is titled Breaking the Header Only Habit, Refactoring C++ Libraries for Faster Builds. And we're going to look at how they took a highly complex graph library that was basically bogged down in this bloated header only state and surgically transitioned it into a sleek, source based static library.
And the kicker there is they did it without breaking a single feature for the end user.
Which is wild.
It's a remarkable achievement, really. I mean, untangling a dense C++ code base is incredibly delicate work.
Yeah. And whether you're a software engineer actively dealing with build times that are, measured in coffee breaks, or a tech-led mapping out architecture, or just someone fascinated by under the hood optimizations, this deep dive is going to give you a blueprint for solving massive technical friction.
Yeah, it's super practical for anyone dealing with scale.
Okay, so let's unpack this. We have to start with the core tension of the source material. It's this love-hate relationship developers have with header-only libraries. Like, why do we even build software this way if it eventually causes so much pain?
Right. Well, to understand the pain, we have to look at the appeal. The author outlines the pros of header only libraries very clearly, and honestly, it is a fantastic honeymoon phase.
Oh, for sure. It feels great at first.
Exactly. When you build a library where every single piece of logic is packed into header files, you give the user a zero configuration experience.
Right, there are no external dependencies to link.
Yeah, no complex build scripts to configure or anything. It's just a drop-in installation. You just copy the files into your project directory, include them, and boom, you're instantly writing code.
The source also mentions they completely sidestep binary compatibility issues, right?
Well,
What developers call ABI mismatches.
yes, that is a major selling point because the user is compiling your library's source code directly on their own machine using their own specific compiler settings.
Uh,
So you never have to worry about whether a precompiled binary from an older compiler is going to clash with a newer system. Everything is baked fresh right there.
I try to visualize it like a massive construction site.
Okay, like a
Like instead of having one master set of blueprints in the foreman's trailer that people have to walk over and reference, you decide to just give every single construction worker their own massive, unabridged encyclopedia containing every single blueprint for the entire skyscraper.
right.
It's wonderfully convenient. Nobody has to wait in line to check a measurement. They have everything in their hands.
Yeah, but to push that analogy further, imagine if every time a worker needed to glance at their blueprint, they were required to sit down and redraw the entire encyclopedia by hand
Oh, wow.
from memory before they could hammer a single nail. That is the hidden cost the author is talking about. That's exactly what the C++ compiler is doing.
Okay, so break down the mechanics of that for us. Why is the compiler doing so much redundant work?
Well, it comes down to how C++ processes code. The compiler works in isolated silos called translation units, or TU.
Yes, got it.
Think of a translation unit as a single source file being translated into machine code. When you use a header only library, that massive blueprint encyclopedia is being copied into every single translation unit that asks for it.
So it's not sharing anything.
Not at all.
Mm.
The compiler has to reparse, analyze, and reinstantiate all of that complex logic from scratch in complete isolation for every single file.
Oh man, so if I have 50 files in my project that need to use this graph library, the compiler's doing the exact same heavy lifting 50 separate times.
Exactly 50 times.
No wonder the laptop fans are screaming.
Right, and the inefficiency doesn't even stop with the compiler. This creates a massive downstream problem for the linker.
The linker. Yeah, the author mentions the linker becomes a bottleneck, and they specifically call out a heavy reliance on manual deduplication flags, like --GC sections. But for those of us who don't spend our days writing compiler flags, what is the linker actually struggling with here?
Okay, think of the compiler as a translator, turning C++ into raw machine code, creating hundreds of individual translated pages. The linker is the editor, whose job is to stitch all those disconnected pages into one cohesive, functional book.
Which is your final program.
Right, because the compiler just blindly generated 50 identical copies of your header-only library. The linker is now staring at a massive pile of redundant code. It has to painstakingly sift through all of it, figure out which copies are identical, keep one, and throw the rest away. It is an incredibly expensive, slow process.
The text even notes this bloat spills over into the developer environment itself. They call it IDE fatigue.
Oh, IDE fatigue is so real.
Like your code editor's indexing tools, like IntelliSense, literally start lagging because they are trying to hold this massive redundant template structure in memory just to give you autocomplete suggestions. It degrades everything.
So the honeymoon is officially over. The project scales, the code base grows, and suddenly your development velocity just hits a brick wall.
Which naturally leads to the big question. If packing all the logic into the header file is causing the compiler and the linker to choke, why not just move the logic?
Right, the obvious fix.
Yeah. Why not rip the implementation out of the header, put it in a separate .cpp source file, compile it once, and just let everyone reference that single compiled file?
That is the logical next step, but C++ throws a massive wrench into that plan. And that wrench is called templates.
Templates.
Templates are the core tension here.
Yeah.
They're a powerful feature that allows you to write generic code like, say, a list that can hold integers or strings or custom objects without writing separate functions for each type.
They are essentially placeholders.
Exactly. But here's the catch. For a template to work, the compiler needs to see the full raw implementation code at the exact moment it is being used, so it can generate the specific version of that code.
I see.
Yeah, so if you try to hide the implementation inside a separate compiled source file, the compiler throws its hands up. It can see the interface in the header, but it can't see the instructions. It doesn't know how to generate the code for your specific data type.
Okay, so we are trapped. To fix the bloat, we have to move the code. But if we move the code, the templates break. How does the author resolve this?
This is where the core solution of the case study comes in. It's a technique called the explicit instantiation pattern.
Explicit instantiation pattern.
Yes. Instead of leaving the templates in the header and letting the compiler randomly generate them whenever they are called, you take control. You leave a clean, stripped-down declaration in the header file, just the interface.
Okay.
Then you move the heavy implementation logic into a separate .cpp file. Finally, at the very bottom of that file, you give the compiler a strict order. You explicitly tell it to pre-compile that template for a specific data type.
Wait, I need to challenge this. Isn't the entire point of a C++ template that it is infinitely flexible? Like, it is supposed to adapt to any data type a developer throws at it. If we use this explicit instantiation pattern to pre-compile it for, say, a 32-bit integer, aren't we just hard-coding it? Doesn't that completely destroy the magic of the template?
That is the exact risk.
Yeah.
And what's fascinating here is how the author threads that needle. If you strictly hard-code every possible type, yes, you do lose the power of templates.
Right.
But the author doesn't explicitly instantiate everything. They focus exclusively on what they define as canonical types.
Canonical types. What qualifies as a canonical type?
It's basically the 80-20 rule applied to data structures.
Yeah.
The author identified the heavy hitters of the specific types the library uses thousands of times.
Okay.
The source specifically calls out core structures like xnetwork : simple graph, standard 32-bit integers, and the bridge structures that connect C++ to Python, like py : : deq.
Oh, I see.
By explicitly pre-compiling just these core workhorse types, the author achieves what they call having the cake you can eat too.
So you get the uncompromised execution speed and the generic flexibility of templates for the types you use the most.
Exactly.
But because they are precompiled in a source file, you completely eliminate the bloat and the endless recompiling. It is a brilliant compromise. Let's look at how the author actually applied this theory to a live code base. The target for this refactoring surgery was XNetwork CPP.
A fascinating test subject. The text describes it as a Network X-inspired C++ plus 14 graph library.
And what stood out to me in the source is the sheer density of this library. In terms of file size, it is tiny. We are talking about 57 kilobytes of headers, maybe 3,500 lines of code.
Barely anything on disk.
Right. But because it is packed with complex, heavily templated graph algorithms, it is incredibly expensive to compile. The objective was to take this dense monolith and transition it into a modular static library, libdexnetwork.a, without changing a single public-facing API.
To borrow from the automotive world, they were trying to swap out the entire engine of the car without moving the steering wheel, the pedals, or the dashboard.
That's a great way to put it. The driver should never know the engine was replaced.
Exactly.
To pull that off, the author designed a phased extraction strategy, or what they call the extraction funnel. It makes sense, right? You don't just rip the whole codebase apart on day one.
No, that would be a nightmare.
You target the biggest, most complex functions first to get the maximum reduction in compile time with the least amount of effort.
It's a very disciplined, structured descent to manage the risk of breaking things.
But the funnel failed, or at least it's hit massive friction almost immediately.
It really did.
Phase 1 of their strategy targeted the biggest chunks of code, anything over 60 lines. Out of this entire complex library, that phase yielded exactly one function, just one, detail : by connected components.
Yeah, just the one.
So they lowered the threshold for phase 2, anything over 40 lines. That only yielded 5 functions. Phase 3 targeted anything over 20 lines, yielding 7 functions. They went after the biggest targets and barely made a dent. Why? If explicit instantiation is the magic bullet, what was blocking them from moving those massive functions out of the header files?
Well, the failure of that extraction funnel exposes a very deep fundamental limitation in C++ compilers. The author ran straight into what we can call the lambda blocker.
The lambda blocker, I saw that in the source. 7 of their largest, most complex functions had to remain permanently trapped in the header files.
Yeah. The problem revolves around how C++ handles lambdas. Lambdas are those convenient, inline, anonymous functions developers use constantly for callbacks or custom sorting.
Right.
But the keyword there is anonymous. Under the hood, a lambda closure type is synthesized by the compiler, and it literally does not have a name that the programmer can reference in the code.
Oh, I see where this is going. If we go back to the golden rule of explicit instantiation we just talked about.
Exactly. You have to be able to tell the .cpp file exactly what type to precompile. If a function relies on a lambda type that has no name, you cannot explicitly instantiate it.
Wow.
You can't give the compiler an order if you don't know the name of the target. So any function that heavily utilized these anonymous lambdas was disqualified from being moved.
They were permanently stuck in the headers.
Yep, forced to rely on the old, slow, implicit instantiation.
And the friction gets even messier, doesn't it? The author didn't just hit language limitations, they slammed into specific compiler bugs. There's a deeply painful detail in the case study about a quirk with MSVC, the Microsoft Visual C++ compiler.
That was a huge headache for them.
I couldn't quite follow the mechanics of why the compiler just gives up. What was happening there?
It is a really obscure parser issue. The author had nested types, meaning a custom data type defined inside another type, and they placed that inside a lambda, which was itself inside a function template.
Okay, that sounds like Inception.
It is. It's a perfectly valid C++ structure, but the sheer depth of the generic types essentially confuses the MSVC parser. It loses track of where it is in the hierarchy and totally fails to resolve types, like type name graph : node _t.
It just gives up.
Yeah, it just throws a fatal error in stocks.
So how do you bypass a bug in the compiler itself? The source mentions a fix using type.
Right, decal type. It's a keyword in C++ that inspects an entity and asks, what type is this? To bypass the bug, the author stopped trying to explicitly write out the deeply nested type because that is what was confusing the compiler. Instead, they pointed decal type at a local variable. They essentially tricked the compiler into deducing the type on its own, guiding it back to safety without triggering the parser bug.
That is so clever. But the sheer amount of manual maneuvering required here is staggering. Between anonymous lambdas, compiler bugs, and line count thresholds, you need a survival guide just to refactor your code.
Which is exactly what the author built. To synthesize all these roadblocks into an actionable system, they created a diagnostic matrix.
A diagnostic matrix?
Yeah, it is a framework to help developers instantly decide what code goes where.
Walk us through how that matrix dictates the architecture.
It is based on 2 axes: size and predictability. If a function is large and uses known predictable types, It gets extracted to the source file immediately. That is your highest priority for reducing compile times.
But if a function is large and uses unknown or callable types, like those anonymous lambdas we talked about,
Then it stays in the header. You accept the bloat because the language forces your hand.
what about the smaller stuff?
For small functions, anything under 10 lines, the matrix suggests leaving them in the header regardless of their types. Not only does it save you the busy work of moving tiny functions, but keeping them visible in the header allows the compiler to inline them.
Which maximizes runtime performance.
Exactly.
Okay, so we have successfully navigated the matrix. We have shattered our single source of truth, taking the monolithic header and splitting the implementation into dozens of separate files based on these rules.
Yes.
But now we have a completely different problem. How do we get the build system to actually understand this new architecture?
You have to rewire the plumbing. In this case study, the author had to reconfigure both CMake and XMake to shift the target. It's no longer just pointing users to a folder of interfaces.
Right, it has to orchestrate the creation of a compiled static library.
Exactly.
There is a wonderfully quirky detail in the source's migration checklist regarding this plumbing. Step 2 of the entire process is literally create a temporary dummy.cpp file. Why are we making dummy files before we have even extracted a single line of real logic?
It is a brilliant structural hack to isolate your variables. By creating an empty dummy.cpp file, you force your build system to initialize the static build loop.
Oh, I see.
It establishes the entire dependency chain. It links up the test frameworks, the Python bindings, the compiler flags, all based on this one empty file.
You are proving the pipes don't leak before you turn the water on.
Precisely. If the build fails at this stage, you know with absolute certainty that it is a configuration error, not a C++ syntax error, because you haven't written any C++ yet.
That saves countless hours of debugging.
It really does.
The way they organize the actual implementation files is just as elegant. The author designed the system for absolute automated discovery. First, they used one-to-one mirroring. If you have a header file named cover.htp, its extracted logic lives in a file named exactly cover.cpp.
Simple and clean.
But the real magic is in the cmakelist.txt configuration, where they use the glob_recurse pattern.
Oh, that pattern fundamentally changes how the team interacts with the codebase.
Because it auto-detects files, right?
Yes. Normally, every time a developer adds a new source file to a C++ project, they have to manually open the CMake configuration and type the name of the new file so the build system knows it exists.
That sounds tedious.
It is tedious and prone to merge conflicts. By using GLO_recurse, the build system automatically scans the directory for any new .cpp files and includes them.
This highlights a crucial shift. This entire effort wasn't just about shaving seconds off of compile time. It was about establishing a maintainable source organization.
Absolutely.
The configuration remains pristine. When a new engineer joins the team, they don't have to dig through thousands of lines in a single header file. They know exactly where the implementation lives, and the build system scales automatically as they add features.
The architecture is finally mature.
The surgery is complete, the engine has been swapped, we mapped the code with a matrix, dodged the MSVC compiler bugs, and rebuilt the dependency chain, but did the patient survive? We have to look at the validation metrics from the case study to prove this massive, deeply tedious effort was actually worth it.
The metrics are the ultimate payoff. The author tracked everything in a build metrics dashboard.
And the numbers tell a fascinating story of the 80-20 rule in action. Here is the final tally. Only 13 core functions were successfully moved from the headers to the source files.
Just 13.
That represents roughly 600 lines of complex implementation code being walled off. That sounds tiny in the grand scheme of software development, but extracting those specific 600 lines completely eliminated the massive template duplication that was choking the linker.
And most importantly, they achieved their primary constraint: 0 API changes. The public-facing interface remained 100% backward compatible for the end user.
We know the logic holds up because the final build passed 87 out of 87 tests, validating across 199 unique assertions simultaneously on both the CMake and XMake build systems.
A total unqualified success.
Which brings us to the ultimate takeaway for the listener. What is the value of going through all this friction?
Well, it proves that you do not have to accept slow, bloated builds as an unchangeable reality of your stack. Header-only libraries are an incredible tool for prototyping and getting a project off the ground quickly, but they do not scale indefinitely.
The technical debt always comes due.
It does. By doing the hard structural work to create what the author calls walled off compiled binaries, you enforce discipline. You separate the interface from the implementation.
Right.
You make your builds predictable, and you drastically lower the operational cost of running your continuous integration pipelines.
Hmm.
You're basically building a technical moat that allows your software to grow without collapsing under its own weight.
It is about maturing a project from a quick and dirty tool into a professional, scalable system.
Right.
So, to recap the journey we took today, we started in the honeymoon phase of zero config header libraries, right up until the translation units and the linker choked on the redundant template bloat. We navigated the extraction funnel, realizing we couldn't just move everything. We hit the Lambda blocker where anonymous types refused to be named. We outsmarted compiler quirks with DICL type hacks, and we mapped out survival with the diagnostic matrix. And we landed on a clean, scalable, source-based build that preserves the magic of templates where it actually counts.
It's a masterclass in pragmatic engineering by the author. But, synthesizing all the roadblocks they had to overcome does leave me with a lingering, slightly uncomfortable question.
No, what's that?
Well, we watched a developer manually invent diagnostic matrices, battle nested type resolution failures, and isolate dummy files just to hide their own implementation details in the compiler.
Yeah, it was a lot of workarounds.
Right. So, if our modern build tools and industry standard compilers struggle this profoundly with Lambda closures and template instantiations, to the point where you have to do all this, is the C++ template system itself inherently flawed for massive scale projects? Or are we, as an industry, simply pushing a brilliantly designed feature far beyond the limits it was originally intended to handle?
Wow, that is exactly the kind of question that keeps systems architects awake at night. Well, thank you for joining us on this deep dive. Keep questioning the friction in your own code base, and remember, just because every worker on the site has a copy of the blueprints doesn't mean the building is going to go up any faster. See you next time.